What's going on, everybody? Welcome to CS540 Week 11. If you're new here, welcome. Be sure to check nearlyblog.com and click this image and you're able to view this page. So this week, we are mainly talking about the clustering. So there are two different methods, really common methods about when doing clustering. One is hierarchical clustering, the second is kmeans clustering. So in this tutorial, I will just use the lecture notes in our lecture to demonstrate. So both hierarchical clustering and kmeans clustering are unsupervised learning. So unsupervised learning is just basically you give a bunch of data sets to your computer and just like let it to just like learn itself. So that is, you don't give them any instructions like this is what, that is what. So all the data sets are actually unlabeled. However, for the labeled data sets, that is the supervised learning. So for example, I give a bunch of images. Some are cats, the other are dogs. I just want to train my neural network to recognize either the picture is a cat or a dog. If you're interested in that kind of tutorial, so I do have one that is in my main page. You click project and you can just click train cat and dog neural network. So this is just basically a TensorFlow neural network that to use to train the neural network and to get a model that is pretty good to recognize the different images, whether it's cat or dog. So I also have the related YouTube videos, and I have very I believe it's very detailed solutions and procedures. So if you're interested, you just do that. So the difference between hierarchical and kmeans clustering is hierarchical. It actually you actually doesn't ask for example, your neural network how many features you want. So features actually the features of the images that you put. However, for kmeans clustering, you actually ask for a specific number of features that you are wishing to get. So for clustering, the really good thing is you can just like to smooth a bunch of data, and you can also classify them. So when given some other data, then it can recognize whether it's normal or abnormal. So it's just like to classify that. So first, let's talk about a hierarchical clustering. So let's say we just have two dimensions, which means we only have two features here. So we just list down their coordinates here. So for hierarchical clustering, it is always finding the shortest point between these data sets, and you actually have different linkage methods. So single linkage is find the shortest distance between the number of cluster and the other member of the other cluster. The complete linkage is greatest, and average linkage is just the average length. So first, let's just assume that we use the simple linkage, which is to find the shortest distance. So first, let's say this is the shortest distance between everything. Okay, so probably I need to mention what is cluster. So cluster is a group of data sets that have the similar properties. So before we classify our data sets, let's say we have n different data points. So before we cluster it, we actually have n different cluster, since none of them are linked to one another. So after the first linkage, we actually have n minus 1 different cluster. And as you can see, when they link together, they will form a cluster. So they're just one cluster with 2 data points inside. And you can also draw the bigram tree. So these are the 2 data, and they form to 1 here. Similarly, we can point out the second shortest way, that is here, and we can also put them together. However, the third thing is, so if we are using the simple linkage, it is actually finding the data point with the shortest path to the data in a cluster. So let's say the lower point has a shorter distance with this, so it will just like combine together, and we just draw them with a higher hierarchy. So the distance that we are using, the formula we are using to calculate distance is to use Euclidean probably distance. So for 2-dimensional, we use that. Also, if we have 3 different features, we can also like to draw all the data sets in a 3D 3D model. So we just calculate that, and we just continuously doing this. And when we finish our since we are drawing this diagram by 2 nodes tree, so when we finish the drawing, we can actually classify them. So for example, these kind of animals here are, I don't know what does this mean, the same here. So you can actually have this kind of diagram and classify them, and when you have a new data inside, you can just compare with this different cluster, and you are able to define, okay, so the new the testing data belongs to which data set. So this is about the hierarchical clustering. It doesn't define how many features you have. So for example, all the green here you can recognize as one class. However, if you like go further, you can actually divide into two different classes. Is absolutely true. So it actually doesn't define how many classes you have. However, what we're going to talk next is our k-means clustering. So for k-means clustering, actually the input is how many data sets we want. All right. So for example, I want 5 different classes. So when we have that, we will randomly pick 5 different points as the center of the cluster. So right now, as you can see, there are 5 red dots picked randomly in a graph. Next is the tricky point. So what it actually is doing is calculate the average coordinate of all the points, or you could say the data sets in that cluster, and to get the value and to set the value as the new center of the cluster. So what it does is typically, so I just use the green color here. So here are the red dots. So you just like connect them and make a vertical value to them, and here is the middle point. So if we only have 2 different dots here, then we connect them. So these are the classifications. So all the data sets upper to this line belongs to this cluster, and all the data sets below this line belongs to this cluster. And you can similarly like draw here and make this a triangle line. Similarly, you can divide it into 5 different groups, 5 different classes or cluster. And you have all the data sets inside. You just calculate the average coordinates and set that as the center of the cluster. After you get a new cluster here, for example, you move from the red dot here to here, then you will recalculate the region of the clusters and recalculate the coordinates of the center of those clusters until the cluster center has not moved anymore. So you're able to get 5 different clusters, which is also for classifying purpose of view. However, the thing here is, for example, manually we can distinguish that there are 5 different classes here very easily. However, when we when computing it, we actually see that the 5 different center point of the cluster is not very good, as we really want them in the center of this kind of cloud or cluster, you could say. So the thing that we can prove is the optimization here is we just want to make them as wide as possible. So as illustrated in this page, so when we pick a random x1, then we pick the second point that is farthest to the current one, and the third one that is farthest from the closer of the x1 and x2, so on and so forth. So that will help us to find the center, to initialize the center points better, and to diversify that better. And so just now we mentioned to calculate the average value in order to get the center of the cluster. There's another way, that is to find the minimized and distortion value. So unlike to taking the average value of those data sets in the same cluster, we are going to find a new center in that cluster in order to make the distortion smallest. So distortion is just the same formula to the variance. So probably, I believe, for this clustering calculation, we just use the word distortion. But in other neural network, we just call that the variance, or you could say the error, the loss. So normally we use the word loss to describe the variance there. So we just want to minimize that. And in order to calculate that, the variance or the distortion, we just take a calculus of the formula. Much harder than this, of course. This is just a very basic understanding, but in real life it's just much more difficult than this formula. Another thing is whether it can find the global optimum or not. The answer is absolutely not. So no matter what kind of algorithm we can't, you maybe can, but it's absolutely not guaranteed to find the global optimum, as normally we just find the local optimum and we just stop there. So that is very common thing. So actually the job for a lot of artificial intelligence people, so they're just trying to get the local optimum as close to the global optimum. If these 2 points actually the same, then it's just a perfect model, I could say that. So that would be like nearly 100%. If for example, if your data set is overtrained and it's just in a local optimum, then absolutely it's not a global optimum. And sometimes the testing accuracy can be really bad, much lower than the training accuracy. The very last thing I want to mention is in order to prevent the overtrains, sometimes we use the regularization. Regularization sometimes is just to plus the distortion with the log of n and times lambda and dk. Lambda can be set randomly, but normally just like less than 1. So this is just regularization is to prevent overtraining. However, this is not very commonly used, as the effect of regularization is not that obvious. So normally we can, for example, use the reduced amplitude or make the learning rate, somehow little. And if we have like training the images, make sure we have a large data set, at least like for me personally, like 10,000 images for one category. And you can also monitor your training sets to make sure that it's not overtrained. And there is a lot of couple of ways. So if you're interested, just view the video. I will also attach that playlist at the end of this video. So if you're interested, just take a look for that. So thank you very much for watching. If you have any questions, comments, please feel free to. Otherwise, I'll see you in the next tutorial.